This video is going to explain the k-means clustering algorithm. So k-means clustering is used to uncover natural groupings within a data set. So let's say that we have a data set consisting of n observations, and on each one of these n observations we have p measurements. So we're going to denote measurement j on observation I as xij. Now, we have to assume that each one of these observations have come from some group, some class. The only problem is we've lost the class identifier. So we don't really know which group each one comes from. So, we have this unobserved variable y sub I, and y sub I is going to be one of the values 1 through big K, but these have not been observed. So a quick illustration of this, if we go over to the scatterplot, I've generated some points, and in this case I've retained the labels. So we have a series of red observations that come from some clump, and we have a series of blue observations that come from a separate clump. But pretend for a moment that we didn't see the red or blue, so the circles or the triangles there, and we just saw a scatterplot consisting of two little clumps of observations. So then the question is, how do we recover these red and blue groups just from the data? So k-means is one way that we're going to be able to do that. Now, I mentioned to you in class that the way k-means is going to do this is to try to find groups that are as homogeneous as possible within each group, and this also implies that the groups themselves are as different from each other as possible. So if we return to the scatter plot, we're going to try to define the groups so that the variation of the points within a group is as small as possible. So I think it's fairly obvious looking at the scatter plot that if we define this as a group and this is a group, that's going to make them as homogeneous as possible. As soon as we start defining groups otherwise, for example, if I were to assign these triangles to the red group, that group would become more heterogeneous. I mean, the other remaining observations would be more homogeneous, but overall we would not have a very good set of groups. All right, well, this turns out to be a very difficult problem computationally, and there is no algorithm that is guaranteed to find the clusters that have this property of being, minimum within cluster variances. The sum of minimum cluster variances must be minimized. So instead we have to rely on a heuristic, and that's what the k-means algorithm does. So what I mean by a heuristic is that it's not guaranteed to converge to this optimal solution, but it should get us fairly close. We just don't know how close we are. All right, so that's going to be a bit of a problem as we will see later, but it's the best we can do. All right, so how does k-means work? Well, k-means essentially involves two steps, and it goes between them after some initialization. So let's talk about those steps, and then I'm going to illustrate this on that data set we just looked at. So we're going to pick some seeds. We have to fix the number of clusters that we're interested in up front. So if in my example on the PowerPoint, we seek two clusters. Okay, so then I would fix k equal to 2, and then I'm going to pick two observations at random to start things off. So if we look at this PowerPoint, I put plus signs on two observations that I pulled out of a hat to start things off. Okay, now what do we do after we've pulled these two observations? Well, here are the two steps that I mentioned to you. The first thing that we're going to do is assign every observation to the nearest cluster centroid. So these two observations that I pulled out of the hat are going to be called cluster centers. Some software calls them seeds, starting seeds, whatever. What we're going to do is find the closest cluster center for every observation in the data set. Now, we're going to do this according to Euclidean distance. Now, Euclidean distance is really measuring variance. The squared Euclidean distance is going to be, the sum of these observations to the centroids squared, and that's really, squared Euclidean distance is variance. Now, once we've assigned every observation to a centroid, then we're going to recompute the cluster centers. So we'll just compute the straight average of all the points that were assigned to that cluster center. We'll evaluate our objective function at this point, and as long as the objective function is declining, we're going to go back and reassign clusters. So let's go look at this for the little data set here. So we are now in projection mode with PowerPoint. Remember, the first step of k-means is to pick some seeds. So I pulled 2 observations out of the hat, and here they are. The step 2 of k-means algorithm is to assign every observation to the closest centroid. So let's just start with this red point over here. What k-means will do is evaluate the distance between this point and this centroid, call that the left centroid, and this point and this other centroid, call that the right one. And then it's going to assign this point to the one that's closer. So clearly this point is going to get assigned to this centroid. Let's consider another point just for clarity. If we consider this triangle way off to the right, k-means will evaluate the distance between this triangle and both centroids. Clearly this triangle is closer to the right centroid. So I've shown which centroid each point is closest to by drawing lines. Now, the next step in the k-means algorithm is to recompute the centroids. So the way k-means does that is to consider all points that are assigned to a given cluster. So in the case of the left one, we got these 4 points. It's going to find the mean of these. And so by finding the mean, it's going to average all the x1 coordinates and then average all the x2 coordinates. And the mean of these 4 points is going to be about here. Likewise, it will do the same for the right cluster. So all of these points must have a center of about here. So let's see what happens. All right, so notice we've moved the center from that triangle, which was our seed, to about here. That was the average of those 4 points. And this centroid drifted off to the right. What do we do next? Well, we go back to step 2. So step 2 is assigning every observation to the closest centroid. And let's consider, for example, this observation. Earlier, this observation was assigned to the right centroid, but now clearly this is closer to this left plus than it is to the plus now that it's shifted. So we're going to change the assignment of this. Let me just show you how that happens. Likewise, all of these points that had previously been assigned to the right centroid now go to the left centroid. What do we do next? Well, we recompute the centroids. So considering all of these points that are now assigned to that plus sign, we find the middle, and it's going to be about here. Likewise, we compute the average of all these points, and this centroid is going to drift a little bit. And so here are the new centroids. What do we do next? Well, we assign every observation to the closest centroid. Here's how we do that. And then we recompute the centers, and notice nothing has changed. Therefore, the algorithm is going to terminate, since the change in the objective function value, so the sum of within cluster variances or those squared distances, however you want to think about them, has not changed. Therefore, the algorithm will terminate.